Hello everyone. For today's journal club, I will be discussing the paper Tackling Inter-Subject Variability in Smartwatch Data Using Factorization Models. So let's first read the abstract. I think you can find the gap sentence.
What is the gap?
However, difference.
I think this abstract is just a very common format abstract that introduces. So I will begin with showing you three user heart rate data. So this is a very simple model and that I just arbitrarily made. And let's say with these three heart rate data, we want to focus on these phases, and we want to see during this time frame, is the user active or inactive? And in human eye, we can kind of guess that the first one is inactive, and second one, during that phase, it increases, so it's active. And then the third one is inactive. However, some models might think differently, and this is because the models will have general baseline for all users instead of having like customized or subject level baselines. So it can't capture differences among subjects. So what this paper does is it kind of sets different baselines for each users, like that. And then it'll pick the right active time frame for that person. And this paper generally uses normalization and autoencoder to capture the subject and population information. So what this paper does is, let's start with a basic raw heart data, which will look like this, and it has two people's heart rate right now. And first, it transforms the heart rate data. So what they do is they get the acceleration of the heart rate, meaning it gets the differences of each time, like this. And I don't know if you can see, but the blue line has a higher peak, and this is because the blue has a higher slope. So it just represents it focusing on the rise-fall speed of the heart rate. And then it always also uses something called relative acceleration, which looks like this, divided by the heart rate. And as you can see, this one, orange, has a higher peak. And this is because this is relative to their own data. So for orange, that orange peak is more impactful than the blue peak. So it focuses on the baseline portion, rise, fall speed. So the model only uses these three data as a starting point for the input. And this obviously captures the speed and then the magnitude of the data. So like other models when we are running, this paper also normalizes the data, and it uses two different normalization method options. So the first, so before I do that, if we have this data, we can represent these data as like this distribution, like this. And what we want to do is a common normalization method is like population-based normalization. So you take the mean of everyone's heart rate and divide it by, and get the standard deviation for everyone's heart rate, and then you normalize. So it has the same pattern, but the scaling is just different. And then this paper uses per subject normalization. So the mu subject is one person's mean heart rate and one person's standard deviation heart rate. So as you can see, like this is a good example where you can see it like moves it closer, so it normalizes instead of having two diverse peaks. So these are the two things that they use. So now we have our normalized data. We go into our train and test set. And this paper normalizes a little differently compared.
Can you so here after normalization, they recalculate the acceleration or they normalize the acceleration? So
They
time is okay,
normalize
yeah.
acceleration.
They normalize acceleration.
Yes. Normalize everything.
Ah, simple variance. Okay, gotcha.
So if we go into train and test, so let's first look at the train set. So during training, they don't use both population and subject normalization. They have two options, and they compare later in the paper. So they both try out population and subject and see which has a better performance. And for train, their method is a little different, but from other papers. But when they have a test data set, they like set a current line here. So it's similar to when we have our like smartwatch data. So based on the current, we will have the past data and then the future data. So in real life, we only know the past data. So that's why we can't really get the mean and the standard deviation for the future data. So that's why we only get the first 60% of the data to get the mean and the standard deviation, like this. And then normalize the test set. And this paper I will show you later, but I just put 60% and 40%, but there's an option to move around the ratio. So sometimes you only have little data, and sometimes you have more data, and you were able to see the ratio performance change.
Your total data length is fixed or also changed?
It's fixed.
To how much? In this example, only 30 minutes. So.
Yes. That's my example, so it's not from the data.
Yeah, other people also can help. Yeah. Can you check the data?
인풋은 약간 타임 시리즈를 잘라서 넣기는 해. 다 넣는.
작은 그 저기 과거가 몇 개월치가 필요한 건지 아니면 그냥 몇 분 단위가 필요한 건지 그거에 따라 되게 느낌이 다르잖아요.
맞아요.
Because I wonder if it's on like a month scale and we need a 60% of month scale that's usually something we do. But it's like a 1 hour scale then
It's
80% of 60%.
one sliding window is 20 minutes.
20 minutes. So in each sliding window they use this approach.
Yes.
Okay. Makes sense. Can we do this only with 20%? No, 20 window. So do you think that U and sigma, the average and variance is the person's average and mean is in each window or
The whole.
whole thing, right? That's right. So then 20 minutes is not key. So the whole is how much? Because to characterize your mean and variance, do we need your 1 day data or 100-day data? It's very different depending. If it just require 1 day, then I'm very happy with this method. But it requires a month, that means this smartwatch working after a month. Fine.
로 데이터를 볼 수가 없어가지고.
플랫폼에서 20분이 20분 동안의 클래시피케이션.
네, 맞아요.
그렇지.
그 시간에 지금 사람이
자는지 안 자는지
움직임이 안
그러니까 20분 가지고 민을 하잖아요. 오케이. 일단 넘어가 봅시다.
So with this process data, we will apply to the model. So this model bases on autoencoder, and we talked about autoencoders before in our other journal clubs, but simply it's made out of encoder, latent space, and decoder, where the point is to extract important features and then predict the output based on that. So the well-known loss for autoencoder is it uses the cross-entropy loss, how well the model predicts, and how well the latent space is able to reconstruct through decoder. So this is the basic structure of the autoencoder.
So, Myna, can you explain a little bit more? What is the difference between reconstruct and predict?
So I didn't include a lot of details for the encoder and decoder part, but so basically you get an input and then the encoder extracts the feature into low dimensional space, which is the latent space, and then that will tell us which features are important and will be able to predict the Y or the output. And the decoder is using this extracted feature, only the important feature, see if it will be able to regenerate the original input.
Yes, so that is reconstruct loss.
Yes.
So what is the predict then?
Predict is
Basically we will compare the X and X hat, how they are similar.
right.
That's the we call reconstruction loss. What about that central pools?
I thought it was latent space, like the low dimensional will be able to predict the output.
What is the difference between that and reconstructed ones?
Reconstructed is, I think, to see if how well the latent space is like not losing any information from the original input. So checking reconstruction is making sure the latent space isn't losing any information, and then how well model predicts is checking if the latent space itself is able to predict the output.
여기 사실 G에서 우리가 원래 하려는 건 클래시피케이션이었어요.
네.
그게 하나 더 붙은 거 아니에요? 붙어서 그게 지금 크로스펜트로이로서 들어간 거죠. 그 G가 G를 가지고 이제 아까 우리가 원래 하려던 이게 어떻게든지 안 되는지 예측하는 모양이에요. 같이 들어가 있고 동시에 같이 피팅이 나가는.
네네. 그러니까 원래 오토인코드는 이랬다. 여기서 이거를 완전 다시 생각이 나는 거예요.
저 이렇게 개념으로
네. 근데 원래는 이제 G가 예측을 예측을 하는 거.
네, 그게 있어요. LC가 왜 들어갔는가.
친구야, 누가 설명 해줘볼래?
그 다음 슬라이드에 내용을 넣으신 거 아니에요?
이거 그냥 되게 원래 그냥 오토코더가 이렇다라고만 보여주는 거라서.
So in this figure, she skipped some additional model structure here. So there should be some more kind of deep learning model structure that predict from G to the output we want to predict, which is, for example, predicting whether this window is active or inactive. So that's why the total loss is summation of LC, which is cross-center fields. This is loss main use for the classification of, and that the construction error is that this is for this auto to reconstruct this original input from the space. That's why we have that.
So then the structural autoencoder change depending on the target we want to predict. The structural autoencoder will change if we want to predict another target.
Yeah.
So we will get another representation of the latent space.
So in other words, the weight of this autoencoder
Yeah.
can be different, or it can be probably specific.
So that the representation of latent space should not be unique. In general?
Yeah.
그렇군요.
So because autoencoder is highly nonlinear,
Yeah.
so I believe even if we predefine the dimension of latent space, there are really so many ways to reduce the so maybe we need to add another
constraint.
Objective here to fix one dimension question.
So that what Yunmin told us was the overall general recap of the autoencoder, how it works generally. And for this paper, it uses something generalized factorized autoencoder. So it, as you can see, the inputs and then the reconstructed inputs, it uses x1, xj, and this is basically contransitive similarity learning, where it compares x1 and xj, and so to explain what x1 and xj is first is x1 is just one window and xj is another window. It randomly selects two windows to compare. So it has all the raw heart rate, acceleration, and relative acceleration as the input.
If we apply normalization.
Yes.
So there were two ways of normalization. Shouldn't it be just the size should be double?
But they don't put both. They pick one.
Okay, they pick.
And then the next part of generalized factorized autoencoder is in the latent space, which looks like this. So what this basically does is it kind of splits the latent space into half. Like one is class and one is domain. And I will provide a very, very simple example to just show you how it works. So we have our inputs, x, y, and xj. And then, so that window will have a class, so whether it is active or not, like that. And then the domain, so whether x1 is from user A or user B, or whichever user it is. And then I'm gonna skip the encoding part, but let's say we have like a latent space that looks like this, so separately. And what this model does is we know that these latent space is mixed of class information and domain information because it's windows based on these, so they're all mixed. So what we first do is just randomly split these. So it doesn't have any information right now, but it'll randomly just split them in half. And our goal is to understand inputs, class, and domain information by optimizing the latent space. And how it does is it brings up a new loss function. So in this loss function, these two values. And then y1jc is, so if they are the same class, so if they're both active, they get 1. And then if they're different, if one is active and one is not, it'll give us 0 value. So if we plug this in, like either one of these sides will only represent the loss. And for us, it's the actives are different, so it'll look something like this. And then the MC it's giving us like a little room on how far apart different classes and domains must stay. And compute the loss.
I think we should understand this equation better. This is key. So this is that entropy.
Yes. No, this is this is added to entropy and reconstruction.
Additional rules.
Yes, additional rules.
What do we mean? The optimized ZC and ZD?
So since these two have like mixed class information and domain information, it kind of creates a relationship between x1 and xj. So
So it's like first randomly split ZI, but is it like to optimize how to partition the ZI?
kind of. So what it does is with class and domain information.
Yep.
With these two, it kind of creates a relationship. So like, if they're similar, they will be closer together, and then if they're different, it'll push each other away.
Mm-hmm.
So that's why it's giving the loss.
지금 이 상황은 클래스 처음부터 얘기를 하자면 특정 레이턴 스페이스의 이 차원은 클래스의 정보를 담고 있길 원하는 거고
네.
두 번째 거는 이제 도메인의 정보를 담고 있길 원하는
네.
건데 그러면 이걸 차원을 그러니까 포트인 코드로 차원 축소하는 과정에서 이걸 토탈리 분리하기 위해서 저 로스를 이제 추가한
네,
건데 그러면 저희가 원하는 건 클래스의 정보를 담고 있다는 같은 클래스를 가진 값들은 이 차원에서의 레이턴스 값들이 모두 비슷하게 원하는 거고 다른 이 클래스가 다른 애들끼리 멀어지게
네네 맞아요.
그래서 YIJ가 1인 경우는 같은 클래스에 있는 경우인데 그러려면 저 GI C 값을 최대한 가깝게 만들려고 로스가 더
그렇게
있어요.
하면 그 미너가 예제를 이렇게 하면 안 되고 어떻게 했어요? 두 가지 예제를 하면서 설명하면 되잖아.
두 가지.
XIAJ가 같은 클래스 혹은 다른 클래스일 때 어떤 경우에 저 로스가 커지고 작아지는지 설명해야지. 해봐. So consider two cases when XI and XJ are same class or different class. In which case this loss becomes higher or lower. If not, you don't understand this equation.
LC 값으로 케이스를 두 개를 이렇게 집어넣는다고 생각하면
네. 한 개는 여기, 한 개는.
그러니까 두 가지 케이스가 있는데 XI, X 그러니까 두 개의 페어가 있는데 같은 클래스에 있는 게 집어넣었으면 LC가 어떻게 나오고
네네네.
다른 클래스가 들어가면 저게 어떻게 나와서 어떤 경우에 저 값이 커지고 작아지는지
So let's do Myna. Let's consider the case Xi and Xj are same class. So that means Yij is
They're the same.
it's right down. So Xi and Xij are same class, then let's write down the equation. That is 1, right? So you don't have to write down.
1.
Simplify that equation.
3.
Oh no, don't write those. Don't.
And this will be 0.
Yeah, that's all. That's the top. Write down the when is the case? X and Xj are same class, right?
Yes.
Write down it. And Xj are same. Thinking about it, what is this loss meaning? When this loss becomes smaller? What's the meaning of that? When
When
this
the
loss
distance between the two are small.
when they become small.
When the difference between these two are small.
That's a good thing or not? Is it what you need?
When they're the same, we want them to be closer.
It's a latent space, right?
Yes.
Because C is class.
Yes.
So you want to make that. We don't care about the D because that's the individual differences, CD. In the latent space, for the class information, we want to be similar when they are same. Let's write down the another class, cases when y is 0, right? That's when they are different, right? So when they are different, when this loss becomes smaller and smaller.
When they're far away.
Yeah. So when G1, GI, GJ difference become larger and larger,
should be larger than MC.
yeah. But MC is the maximum value, so G1, GJ differ, then that LC becomes smaller, right?
Yeah.
Why? When they are different, which points are different in the latent space. Okay. Here, so here randomly split means, let's say our low dimension space is 10. Among that 10 dimension feature, we don't know which one is class, we don't know which one is subject. How to do? Maximize this is the best choice, isn't it? Okay, so I think this is a key idea of all this paper. So let's imagine that we have only 2-dimensional lattice space. Okay. Let's say the white is class 1, red is class 2. Then x-axis, y-axis, what will be the class dimension? What will be the subject dimension?
X-axis
X-axis should be class, and then y-axis will be domain. Does it make sense? So, in that kind of, if we choose both, then due to this thing, this error will become larger. Right? Only when we choose this x-axis, then perfectly satisfying, minimizing this loss. Does it make sense? So, Myna, when I ask you plug a certain number, it does not mean doing the 산수. You should think about this kind of meaning. So without it, we cannot understand the equation. You get it?
Yes.
Okay, good.
So
Can I have a question?
Sure.
So is it the MC is also the kind of parameter we choose too?
So it's giving more. So usually, let's say like it usually gives higher loss, but by having a little, you say, lenient, it doesn't give you like the full penalty. It only gives you some.
로스가 아까 너무 튀지 말라고 그냥 설정으로 그러니까 그런 거 같아. 계산상 컴퓨터로 돌릴 때.
근데 그럼 결국 그 로스끼리 더할 때 그 쟤도 그 레귤러라이징 벡터 같은 게 되는 거야. 또 레귤러라이징 벡터 하나
그러니까
So far we have
그렇지
three
그게
laws.
맞지.
Construction loss is just for autoencoding. I think entropy loss will be how accurately we classify the person. And this third most kind of
We need to divide. I think this is the main point is that
divide.
fully divide.
Yeah. So another advantage of having this is actually for the latent spaces. Kind of G1, G2 could be this as well. Same two dimension. Okay, maybe both could be okay for the prediction. Okay, but because anyway, both the same information for both, we can predict class accurately. There's no differences because just thinking about it, defining this coordinate. I know this looks better in our eye, but in terms of computer, using this axis, we can completely predict this point location the same way, right? Just we need to multiply like A. So for the just entropy loss, there's no difference between this and this. But due to the third loss, we try to make the axis, which is separate the class and subject. So kind of that's the key idea of this.
So I only, in this slide, I only have example when the classes are different, but I will show you what I have. So similar to domain, similar to class, domain loss will act as the same way, where when the class is the same, it tries to pull it closer, and then when the classes are different, it tries to pull them away by giving more loss.
Let's think about it. What's that loss? D is about the person, right?
Yes. User.
Okay. If they are same class,
MD
마이너스 거기서 same
same loss.
아이디어가 same 건가?
same loss.
그래서 되나? 맞나? 이상한데?
서브젝티브 디퍼런스도
D가 sorry.
네.
Here is D.
Yes.
Okay. So I see. Because the data, many data come from the one person. Because we have many windows.
So in this video, we are going to separate it horizontally, and we expect that the upper one is from the same one.
person.
Yes.
See, you mean it's good? Hopefully, this person is Yunmin, this from Hongju, this from the Myna. Then this also will be minimized, I think. Along that axis. Y-axis, Dongju has no differences. Right? So the key is, if you look at the y-axis, Dongju no differences, right? Y value. But Yunmin has no differences. So that's the when this become minimized. But if we look at the Yunmin and Dongju, we try to make sort of the far away. 다른 사람이면 다르게 맥시마이즈 하는 게 좋은 거 같나? 그건 모르겠네. 같은 사람이면 같게 하는 거는 자연스러운 거 같은데 다른 사람이면 다르게 해야 되나?
이걸 나눠서 뭘 더 하나가 좀 궁금한데.
그러니까
지금 나눠서는 나누는 것만으로는
근데 이건 없었어야 돼가지고 이게 왜 있는지가 이상한데. It will be weird.
고작
Because it looks
20.
like using people as Gaussian distribution, right? Kind of. You mean heart and my heart rate? That different? Although we are different people.
그렇게 하면 오히려 완전 새로운 사람이 들어왔을 때 오히려 안 좋을
Okay. I'm a little bit worried about this term. This term makes sense because in single person, it should be similar. That makes sense. But this term makes all of us as far away each other. Do we really need that? 저건 좀 이상한데?
근데 이거
So
인풋을
this is okay because it's a different class, then we should make it different. But different people, do we really have to make all people are that different?
인풋을 노멀라이즈 하고 넣은 거예요. 그냥 넣은 거.
노멀라이즈 하는 거지.
하고 넣었어요.
그러니까. 이상하다.
좀 이상하긴 한데 그게 좀.
아니. I bet if we delete this, it will compare it. It's a little bit weird. Yeah.
그러니까 굳이 떨어뜨릴 필요가
없지 않니? 너랑 내가 뭐 그렇게 다르겠노 심지어. 그러니까 이상한 사람이 있겠지. 근데 그 몇 명을 떨어뜨리기 위해서 비슷한 인간들 다 떨어뜨리는.
그러니 굳이 멀리 떨어뜨릴 필요가
그렇지.
없을 것 같은데.
우리 AI 전문가님 어떻게 생각하십니까? 왜 딴 데 봅니까? 안 이상해? 아니 모르겠네. 그래서
이제 그림 뭐 만들어긴 했네요. 한번 같이
하여튼 그러니까 이거는 완전 make sense. 왜냐면 다른 클래스인 건 다르게 하는 건 오케이. 근데 이상한데? 오케이 가보시죠.
Can I have one
Yeah,
more
sure.
question? So here, we split the latent space variable randomly. So is it randomly split it just once, or is it randomly split it every iterations or some iterations?
It's randomly split once for one input. So if they have x, y, x, j input, it'll just be randomly split once.
Okay.
Tune.
Okay.
So since there's loss for both of the cases, what they do is try to separate them apart from the loss. So it was 0.4 and 0.5 as a class, but since they were different class, it tries to pull them apart. So maybe something like this, and then similar to domain. And if we kind of visualize based on the ZC and ZD plane, we have our original ZI, which is right here, and then original, ZJ. Based on the loss and then new optimization, it'll kind of push them away like this. And that's where, and I also included the new total loss that they introduced. So our cross entropy and then reconstruction loss is still there, but they add the class and domain loss into it. And they kind of iterate and hyperparameter tune until they're kind of like far away from each other, like this. And this is just for one x1, xi, and xj case. And after they did that, they repeat this process for other window combinations. So, like, they will have something like this, and then basically something like this, where it just kind of divides and it understands the connection of the domain state and then the class state.
여기서 노란색 같은 사람인 거고 초록색도 같은 사람이에요.
아니, 이거는 그냥
노란색과 초록색 하는 거예요.
그냥 뭐지? input 1 and input 2라고 생각.
그러니까 인풋을 페어로 집어넣으니까
맞아요.
그래서 지금 그렇게 표현을 한 것 같아요. 그러니까 한 번에 두 개의 인풋을 딱 집어넣으니까 한 번 할 때마다 툭툭툭 이렇게.
근데 여기 노란색 초록색이 같은 클래스랑 같은 사람인 듯한 거예요.
네, 그건 아니에요.
그냥 표현하는.
But can I have one more question? So the cross entropy is also based on the classification, right?
Yes.
then we have two terms from the classification rules.
Oh, are you talking about this like?
Yeah,
The
class separation.
But it's not predicting it's not classifying the loss class is not classifying, but cross entropy is for classifying loss.
가까운 느낌인 것 같아.
그런 느낌.
So this is one of the methods that they used, and then they used a second method which is called a triplet factorization. So it basically, I'll just show you how they go about this. So it has 3 windows this time, and they each have a name. One is like the base, the anchor, and then the second one is called positive, and the third one is called negative. So as you can see, for the base, the positive needs to have the same class as the anchor, and then the negative needs to have different class as the base. That's what they put in for their inputs. And then they kind of repeat the same process again. So I will go over this again, and I will try to like what Professor suggested.
흔하게 하는 방법.
앵커랑 포지티브는 가깝게.
So
세개 사이. IJK가 여기 있는
so let's say this is our anchor, so it's class 0, and then we have, let's say we have J, let's put CK, and this is 1, and let's say we have, so in this
all
class,
these are different people?
it depends, but for right now, we're only looking at class.
Class, so they can be either same or
Yes,
different people?
yes.
Okay.
So let's say we have our like random latent space that looks like this. So since they're the distance from here and here, and then we look at distance from here and here, because this is our base. And then we see that the different classes are closer than the classes that are the same. Then we give the higher loss.
Okay.
So this is like the centerpiece, and then compare the two differences between K and J.
느낌 뭔지 알겠는데. 좀 이상하네. 이게 앵커를. This is anchor.
네.
GIC anchor.
네, 맞아요.
So GJ, GKC could be 2, but they are always 1 and 2, or they could be 1, 1 or 0, 0 as well.
So J needs to be same as I, and K is different from I.
I see.
그런
So-
페어, 모든 페어들에서 계산하기.
Same and different.
Yes, yes.
Oh, okay. So kind of you wish same class distance should be shorter than
Shorter than this, different class.
또 그거야. 네. Anchor could be also every point.
Yes.
So, is it simultaneously with the previous
No,
or
they're compared, two different
Ah.
ones, yes. There's totally separate ones.
So previous loss or anchor loss? Or like previously there was one loss.
Yes, we don't use that. This is a new class loss they're using. So they're using two different methodologies.
Okay, so this is equation looks a little bit simpler. So the point is, if we are kind of for every person, we try to make the similar class is closer to the. Okay.
So I will kind of skip the plugging in part, but for the domain, they do the same thing again. This. And then they just basically update with the new z latent space variables based on the losses. So I think visualizing might be better. So we have our zi value like this, zj and the zk, and then based on the new values, it'll again move them apart. And then what this shows is that I and j are the same class, so they're in the same sense. And then zi and zk are the same domain, so they'll have like a same domain line. So we can kind of see the relationship from the losses. And again, we repeat this for all the other window combinations. So just like randomly like this, and then separate class and domain latent space. So that's how they explained their model and their loss, and that is the final loss for the TFA.
So here, should they check all combinations or is there any some
There's
selection
like,
of anchors?
I remember reading like there's a mini batch. Use all combination mini batch. So that was the end for their methodology, and I'll show you the results. So NLP is just a multi-layer perception, just a regular deep learning model, and this is again what we talked about when train is using population-based and train is using subject-based, and then we can see that GFAE has the highest performance.
Which one is best?
GFAE when ND equals 0.
What is GFA?
The first.
This one.
This one, yes.
Generalized factorization. What is the meaning of MD equals 0 or MD is not 0?
ND equals 0 is when we had this, the MC and MD equals 0. Or MD equals 0. Minus.
It's multiplication then. It's exactly kind of MD equals 0 means 이런.
저 처음에 신경 안 썼던 얘기.
1등이 뭐였어? MD가
네,
0이 돼요?
네.
지금 안 됐지.
그 LD 자체를 안 써도 굳이.
근데 저건 오타가 맞는 것 같기는 한데.
네, 맞아요.
어떤 거니? 이렇게 논문 그림 이렇게 돼 있었어?
아니 쓰기만 쓰기만.
쓴 거에도 더 좋은 거네? 뭐네? MD equal 0 이거잖아, 그렇지?
그러면.
MD를 다른 사람은 다르게 만드는 걸 했을 때 베스트라고? 몰랐네.
이게 잠깐만요. 근데 이게 AUC가 트레인 AUC가
이거
트레인 테스트가 어떻게 하는
테스트했던 것 같은데.
레귤라이션 있을
테스트할 때
때도
아예
잘
새로운
된다.
사람을 넣지
그런 말
않았던 거
하고
맞아요.
아,
밸리데이션 느낌 아니고 진짜 그냥 스플릿만 하는 느낌.
그런 거
근데 저 점선이랑 실선
점선이랑 실선 I didn't go over this, but I will show you. So, 그러니까 원래 normalization 할 때 they're using resting heart rate as a normalization.
아 그게 실선
점선
점선
실선 is just the model that I introduced.
이게 그러니까 지금 이게 잘 되는 이유가 어떤 느낌으로 받아들여지냐면 원래라면 사람별로 모형을 학습하는 방법은 있어요. 사람별로 모형을 학습을 할 수도 있잖아요. 트레인 테스트가 아니라 앞부분 뒷부분 나눠. 이거는 모형 하나로 하는 건데 아까 그 로스를 더함으로써 레이턴트 스페이스 안에 구획별로 사람별로 이렇게 나눠버리는 거예요.
그러니까 새로운
그러니까 그러면 잘 안 될 것 같고 기존에 했던 거는 사람별 그 차이를 보장해 줘버렸으니까 정확도가 더 높게 나온다 이렇게 된 거예요. 그러니까 이거는 어떻게 보면 사람별로 모형을 따로 학습하는 대신에 하나의 모형으로 여러 사람별로 여러 사람을 구분을 하면서도 정확도 높일 수 있는 그런 모형을
그래서
만들겠다.
제가 느끼기에 이제 이미 핏빛을 차고 있는 사람들을 통해서
네.
그 데이터를 가지고 모델 돌린 다음에
네.
이제 미래를 이제 바로
네,
알려주는
사람의 미래는
맞아요.
예측이 될 것 같아요, 확실히.
그런 거 같긴 해요.
네, 근데 아예 정보가 없는 사람은 안 돼.
안 될 것 같아요.
그걸 안 되겠지.
네,
그래서 그게 중요하다니까 이게 약간 하루는 되는 건지.
그렇죠.
그러니까 이게 6개월짜리 데이터 쓰는 거는 쓸데가 없는 거고 그냥 6개월 동안 알고리즘 작동을 안 한다는 얘기. 근데 하루 정도야 뭐. 그래서 그 데이터의 길이가 이거의 유즈풀리스를 결정할 것 같아요.
그 약간 플로우 매칭할 때도 컨디셔널 플로우 매칭이가지고 그러니까 컨디션 별로 퍼지게 하면서도 모형 하나만 쓰는 거 있잖아요. 또 똑같은 아이디어인 것 같아요. 근데 중간에 그 레이턴트 스페이스의 레귤러라이제이션을 하는 거를 더함으로써 약간 컨디셔널하게 그 모형이 작동하도록 만들어버리는 거죠. 그런 느낌으로 받아들이면 될 것 같아요.
So NLP is their reference performance.
Perceptron.
Yes.
So
They-
perceptron is the most simple
Yeah.
풀리
classification.
커넥티드 네트워크.
So that is their only rival kind of.
Yeah, only one. They compare them.
뭐 모델 두 개
많을 것 같은데 모델
했으니까.
조금 많을 것 같은데.
그렇게 뭐 차이가 많이 나는 것처럼 보이지만
그러면
헬스보다 훨씬 낫긴 하니까.
실은 몰랐을 것 같아요.
이게 그 뭐지? 레스팅 하르트
아,
를 평균을
I think it's maybe it's like different standardization, different normalization. They got some baseline of
이게 그
something like
처음에 테스트할 때 아무도 없잖아요.
yeah.
그거에
I think there's some explanation of in appendix, but I can't.
그래서 진짜 딱 한 사람의 미래를 예측하는 그런
그거지 새로운 사람은 아닌 거지.
네.
오케이. 근데 어쩔 수 없지.
네, 그렇죠.
Because this is anyway any personalized method without he or her information we cannot do anything. But it's okay to assume that we need a certain information for individual to predict something. But hopefully what we can do is this latest space can be used for anyone. When the new person comes, let's say we're recording one day his information, and then we don't need to train all this model. We just send into this space without retraining the Z1, Z2 thing. Then it's useful.
Summary, I think the main things were just what data they used, and then the two normalization methods, and then the latent space split methodologies for the models. Yeah, so thank you.
Yeah, any question, please?